A pretty common robotics challenge is building some sort of boom arm on a pivot so that it can rotate up and down and then hold its position while it's at any motion along that pivoting or revolute joint. And today I'm going to walk you through step by step on how you can not only build one of these pivoting arms and things to keep in mind and what kind of sensors to use, as well as how to actually program that too so you can have an arm that's able to pivot and hold its position at any angle that you choose. Now, I've been teaching robotics for over a decade now. Let's skip the fluff and get right into how exactly we're going to do that. So when it comes to making a robot with a pivoting arm, we're going to talk about a robot overview. What sort of sensors are you going to need? What sort of motors might you need? What sort of setup might you want to do? How might you think about gear ratios? How might you go about calculating that to be able to do some pivoting arm? I'll go over some general sort of principles and some things you're going to want to have in your robot before. I'll also share with you one of my CAD files that I have so that you can build along with me if you want to build the exact robot I'm going to be using for this setup. Now, you don't have to have the exact robot for this. As long as you go to a robot that has some sort of pivoting arm mechanism, you will be fine for following through on this tutorial. Then we're going to go through what exactly is PID, or proportional integral derivative control. What is a feed forward, and how do we compensate that for gravity depending on what angle our arm is currently facing at? I'll walk you through that step by step through the kind of logic flow on how a PIDF controller works, so that removes a lot of the mystery that comes up behind what these controllers actually do. And by the end, you'll understand it pretty well. Then we'll get into actually programming that pivoting arm class. I'm going to be programming this in Java using the Rev Robotics Control Hub. That's something that's typically used in FTC robotics. But of course, the logic works the same whether you're using Python, C++, Arduino, whatever have you. Despite being written in Java, the main methods, variables, and logic works the same. If I were to start speaking Dutch, it might be a different way of writing it, but the logic and the intention is still there. We'll talk about all the necessary variables and methods that you're going to need to get this thing set up. We'll go through actually designing that PID loop and that gravity compensation for once you understand how it works. We'll walk you through step by step and how to actually program that. And that'll also show you how you can use that class inside of a Teleop program so you can actually have this thing up and running. Now, once you have it programmed is not quite enough. You also have to actually tune your PID because you can't just take my values for my robot and plunk them right in on your robot. You need to tune your robot in such a way that makes sense for your specific setup. And I'll walk you through the logic and the flow of how you actually tune for your specific robot and your K-gravity as well for those constants. Now, the nice thing is, with that tuning process, it's as much of an art as it is a science, so it's a bit of a feel thing. And I'll give you some of the best tips that I have for tuning PID controllers, and it'll make it a lot easier for you doing your own tuning process as well. And then lastly, we'll put it all together. Once everything's all run up, all tuned, all programmed, we can actually run your arms. You can actually have your full class moving up and down as it is that you need. Now, let's talk about the base robot chassis we're going to be using to be able to move this robotic arm up and down. Now, the actual main arm itself is a telescopic lift from Offset Robotics. Now, this does telescope out, but for this tutorial, we're going to be assuming that we only have a fixed arm here. So we're not actually going to adjust for having different distances of the length of our arm. I've got a different tutorial on that. When it's finished, I'll have it linked in the description down below. But as far as how this arm goes, this whole arm here pivots up and around this large central joint up here. And this is driven by a single motor through a gear ratio on this axle, which then gets driven to this axle up here with these gears. And then this is the actual axle that arm, of course, pivots up and down on. So let's get a little closer look at this axle itself here. So it all starts with this motor. This is a ultraplanetary from Rev. I'm quite a big fan of theirs in that what it allows you to do is you can get these little sort of pods that just kind of stack on top of each other, and it makes it quite easy for you to be able to change your gear ratio over time. Now, this is a 6,000 RPM motor that goes through 3 4-to-1 reductions on a planetary gears. So the output of this motor here is 64 to 1. So for every 64 revolutions of this motor, I will get a single revolution of this point here. But that does mean that despite being 64 times slower, we are 64 times stronger over on this axle. Taking a closer look at this axle here, I have a large 7mm shaft that is coupled to our motor shaft, and there are two 20-tooth gears here. Just above are two 100-tooth gears on another axle that are supported by these kind of side braces. So I have, not only do we have that 64 to 1 reduction, we also have another 5 to 1 reduction. So every 5 rotations of this gear, we'll get 1 full rotation of here. So we have about a 320-ish total gear reduction in this entire system by the time we're actually done running through that. So as this motor rotates, we can actually see that it rotates quite a bit further than this actual eventual output shaft does. I'm running into my tools to be able to actually do that pivot for the arm. Now, one of the big things that we need on this system is we need to figure out, how do we know when our arm is at rest and at the bottom? There's a couple ways you can do that. The first way you can do that is something called a motor encoder. And on the side of our output shaft here, where we have our 100-tooth gear, this is the main output or pivot shaft for our arm itself. And what I have is I've attached here a rotary encoder. And effectively what this does, this has a little magnet inside of it. And as this shaft, this white shaft rotates around, as this arm pivots up, this encoder on the inside is actually keeping track of where this is relative to where it is that it started. So we can actually keep track of how many ticks or how many rotations this little device has made to be able to figure out what angle we have on this. Now there is an external rotary encoder. I've put this on because it makes it a lot easier for me to find the angle. You do not need an external rotary encoder though. You can, of course, just use the rotary encoder that is on the back of the motor itself, because on the back of all these rev motors, they also have a rotary encoder. One of the problems with using a rotary encoder here is that I find it makes it a little harder to abstract out some of those challenges. And why I'm using an external rotary encoder over here is this encoder is one-to-one with this arm. This encoder has our large gear reduction, plus we have an additional gear reduction we have to end up running through. So it ends up meaning we have to do a little bit of more math with our gears to be able to find those, that I personally find it's a lot easier just to have a one-to-one reduction, one-to-one encoder on the outside here. It's absolutely not necessary to have, but it's definitely a nice to have a through bore or through axle encoder in this scenario. Now this through bore is from East Loop Components, but you can also get through bores from Rev as well. Rev Robotics, which is another great way of going about it. Now, another way or another safety check that I always like to put in is you need to know some way more mechanically when your arm's at rest. It's always possible that your gears slip. You might have some slop in your system. Now, of course, it's best if you don't have any slop in that system, so that as this arm is pivoting up and down, it's not possible for the gears to slip, but crazier things have happened. So I have a Hall effect sensor at the bottom here to be able to know when our arm is at rest. And what a Hall effect sensor is, it's effectively a magnet sensor. So this is a new product from AndyMark. It's a magnetic switch from AndyMark, and I'm quite a big fan of their Hall effect sensor. It's got a little 3D printed case, so it makes it easy to be able to swap that out. I've also found that of the Hall effect sensors I have used so far, it has quite a reliable width in which it's able to actually trigger. So we have a large thick magnet here that I have put a bolt through and attached it to my piece of channel, so that as this comes down to the bottom, our Hall effect sensor actually turns on. I'm going to flick on the robot here that you can see this red light as the magnet goes away, and as it comes towards it, we can see that it actually starts to trigger off and trigger on, off and on. And it's got quite a wide gap from the sides that it's able to actually trigger as well, which is why I quite like this sensor too. So you don't need a Hall effect sensor on the bottom of this thing to be able to know when your arm is at rest. However, I'm personally a fan of having a few more sensors than I need on my robots because it does make things a lot safer and a lot more reliable because you know when your robot is in a state that you would not expect it to actually be in. This also allows us to reset those encoders, so those encoders will go back to 0 when this thing actually brings itself down to 0, which is a really helpful thing to be able to do in your robotics projects. Now, if you want to build this exact model yourself, I've got the CAD files in the description down below, as well as the code snippets that we're going to be making in the future here. So let's talk quickly about what our PIDF loop is actually all about. And PIDF stands for proportional integral derivative, and feed forward. And we can effectively use these 4 different values to be able to update what we want our arm to do. So let's talk about what proportional does in a rather basic way first. So let's say, for example, we have our arm and it's capable of rotating up and down along this axis, and we want to get it to this imaginary goal position. If our arm were really far away, we might have a really large proportional control response. So the farther away we are, the faster we're going to go, or the bigger the motor is going to be. Now, let's say, for example, we are here and we need to get a little bit closer, but we don't have as close of a distance to go anymore. So in this case, we're going to have a much smaller proportional control to be able to get ourselves there. So proportional is probably the easiest one to understand because effectively what it does is the farther away you are, the more power you use, the closer you are, the less power you use. So our power is proportionally scaled to how far away we are. When it comes to integral control is really used for getting ourselves to a steady state. The problem with a proportional control is that eventually over time, what's going to happen is if we want to get ourselves to this goal position, we may eventually get to this part here, and we only have such a tiny little gap that we need to eventually move ourselves towards to get ourselves to our goal. Standard proportional control will rarely ever get ourselves exactly to that goal, because what will happen is if our proportional is too high, we'll actually end up overshooting, and then we have to come back to our target. Or if our proportional is too low, we'll actually end up undershooting, and then we don't have enough power to get ourselves right to our goal. So that is where that integral ends up coming in. So effectively, what an integral does is it is a sum of our error over time. So if our error is effectively what's going to happen is as we get closer to this, we're going to start adding in the cumulative error that we have. And let's actually take a step back and talk about what our error is. Our error is that distance between where we are compared to where our goal is. So our error is always our goal minus our where we are. So that is always what our error is going to end up being. And with integral, it allows us to get rid of these really small errors. Like let's say, for example, our error might be, we are 0.1 degree off of our goal. So we're never actually fully going to get there. So what our integral does is starts to add up this error over time to be able to add more power to our motor. So if we are sitting right here and we look at our integral as power over time, on some sort of chart, we're eventually going to have we're going to start with a really low integral over time, and eventually we're going to start scaling up and up and up and up and up until we get to the point where we have enough power that we've added to our motor in order to reach our goal, and then we should stagnate out with our integral to be able to reach that point. So this allows us to basically get rid of very small errors that are close to our goal without actually shooting there. So with derivative, effectively it looks at our rate of change or the amount of speed at which we're going. So if, say, we're going to look over time, let's say we look at 20 hertz cycle, and in our first flashback, we end up shooting from here to here, and in our next cycle, we end up shooting from here to here. So we can see that maybe this was a 30-degree correction, and this one is only a 15-degree correction. So with our proportional control, we're making bigger jumps and then we're starting to make smaller jumps. So what derivative is doing is starting to look at our rate of change. So our rate of change might start really high and then it starts getting much lower as we get towards our goal. So derivative is our damping force. So it allows us to slow down as we get closer to our target. So rather than, say, if this is our goal, rather than quickly shooting right to it and overshooting, what it allows us to do is allows us to hit it and then ramp down our speed until we get to that goal. So rather than shooting something that's linear like this, we may end up with a much nicer curve. So you can think of derivative as some sort of ramping force to be able to get there. And then the last thing we're going to be adding to our system in this more simple example is going to be our feed forward. And our feed forward is going to be a constant value that we're going to add in to be able to adjust for our speed over time. And effectively, this is actually going to be fighting the force of gravity because we have a robotic arm and it's pivoting around this center axis. And if we are, say, up to this point, the force of gravity is not that high because our arm doesn't really have much force being placed upon it. If we were to draw an area under our triangle here, we don't have much of a shadow being cast. And you know this intuitively. If you are a person here and you put your arms out at your side and they're really close to your body, it doesn't take a lot of force for you to be able to stretch this out. But if you put your arm directly out to the side, this requires a lot more force than this does to be able to pull that out. So in this case, if we have our same pivot arm and we are directly like this, we have our maximum value that gravity is going to be trying to pull ourselves down when we're about 90 degrees from or directly parallel to our horizontal or our ground plane. So our feed forward is going to be a constant value that we're going to add in to be able to effectively fight off the force of gravity. And all we need to know is what is our angle relative to the ground plane to be able to know that if we are at directly 90 degrees, we should be applying our full gravity feed forward. If we are straight up and down, we should be applying no gravity feed forward, and any place in between, we should be doing a little bit less. So that's a sort of high-level view of how our proportional, integral, derivative, and feed forward in the case of gravity is going to work. Now let's take a look at this when we actually do our main update loop for our arm. So let's start with calculating our error because that's really important. So that's the first thing we are actually going to calculate out is our error here. So we need to know is where are we? So we're going to say we need to basically figure out where are we. So we will read our encoder to sort out where are we. So basically, this is basically where in this space relative to our goal is our encoder. Then we'll calculate our error. And our error is, of course, equal to our goal minus our we are at. So wherever we want to get to minus where we currently are. Then we can talk about applying our proportional control. And our proportional control is actually quite simple. Oops, I cannot spell today. Proportional control is quite simple. That is simply our P term, or what we're actually going to apply to our motor is our error multiplied by our Kp, or our K constant. And this is just a value that we're going to tune later that basically multiplies it. So if we think of our motor as allowing anything from negative 1.0 all the way to 1.0, if our Kp, well, let's do an example. Let's say in this example, our error is 10 degrees. And we have a Kp of, in this fictional example, 1. If we had an error of 10 and we took error multiplied by our Kp, that would give us a value of 10. We're already way over what our maximum value allows to apply on a motor. So a Kp of 1 would be way too high. That's not going to work. So we might instead say something like 0.001. And what this would allow us to do is now, if we have an error of 10, it means we're starting to get pretty close to our target. 10 multiplied by 0.001, that means we're now only sending 1% power, closer we get to. So maybe this is a little bit low. We might have to get it back up. But you see why our KP is actually quite a bit lower of a number, because our motors only accept a value between 1.0 and -1. And that's all we need to do for our proportional control. If we were just making proportional control, all we would do is just simply say that our motor power is just going to be our P term, and we would be done. Very simple. But we can't actually do that yet. So now we're actually going to start computing our integral. And to be able to do that, we need to go back up above in this chart to start figuring out something a little bit sooner. And at the top of our chart, the very first thing we're going to do, or above that, is we need to get something called delta time. And delta time is basically the time that it takes since our last loop. So this one is going to be effectively our timer dot seconds. And this will keep track of how long has it taken for us to go through one full loop of our system. And then we will reset our timer. So this keeps track of our timer over time. So now we're going to figure out what's our current time. We're going to reset our timer so that when we come back to the loop, we can get the current time, reset the timer, and then we know how long it's taken us to get through a loop. Now we can start doing our actual integral sum here. So our I sum is going to be equal to, and we're going to basically clip or bound this between a few different values. We're going to say our I sum plus the current error multiplied by that delta time, or how much time is taken since the last loop. And then it's going to be our plus slash minus our max I sum. So effectively what this is going to do is it's going to take our current I sum, it's going to add in our error multiplied by our delta time, and then we're going to bound it between some sort of maximum value for this I sum so we don't get any sort of crazy high integral windup. Effectively what can happen is if your integral sum gets too big, when you go to make a change later, you can think of it kind of like a spring. And that spring is winding up, winding up, winding up, winding up, winding up, winding up, winding up. And the higher this value is, when it comes time to flip back the other direction, effectively, you can have this huge overspike or huge swim. So we're going to again tune this later. This is a bit of an arbitrary value for now, and that will allow us to get rid of that kind of spring windup. And then our I term, is just similar to our P term, is equal to our integral sum multiplied by our Ki. And similar to our Kp that was quite low, our Ki is also going to be probably quite low. In fact, even quite a bit lower than our P term actually was. And now with our integral term figured out, now it's time to actually start do our derivative control. So the first thing we're going to check is we are going to check if delta time is greater than 0. And it is entirely possible, not entirely possible. Sometimes your loop can be so fast that you actually have a delta time of 0. And because we're about to divide by delta time, we can't actually divide by 0. So we just do this as a safety check. And in this case, if our delta time is greater than 0, or in this case it is true, we're going to say that our delta term is going to be equal to our error minus our last error, whatever that previous was, because this is that rate of change, divided by delta time. And we're going to take this whole thing and we're going to multiply that by Kd, or whatever that K, whatever our derivative constant is actually going to end up being. If our delta time is false and we have it, or this is actually 0, we're just going to set our D term is going to be equal to 0, and then we'll move on. And then at this point, we'll set our last error is equal to our current error, so we can adjust again for that rate of shift over time. So that's a whole whack load of stuff. Let's go back through that really quick. So at the start of our loop, we're going to catch our current delta time, which is our timer dot seconds, and then we're going to reset that timer so that when we come back to the loop, we can figure out how much time has passed between loops. Then we need to figure out our error. We figure out where we currently are, and we say that our error is our goal minus where we are at. Then we can calculate our proportional control, or a proportional term, which is effectively our error multiplied by our Kp. Again, we're going to tune this later. Then we'll get our integral sum, which we're basically going to make some bounding ranges so we don't go too far, is going to be our current sum plus our error multiplier dt. So whatever error currently is and how long it took for that one to previously get there. And we bound it between our I sums. And then our term is effectively our current integral sum multiplied by our ki. Then we start getting into a derivative of our damping force, and we're going to check to make sure we have a non-zero time. If we do have a non-zero time, we're going to take error minus our last error to figure out that rate of change, divide that by the delta time and how much time that loop has happened, and then we'll multiply all that by our KD. And then we'll set our last error to our current error. So that is our PID controller, or our PID term. And effectively, this is going to be our P term plus our I term plus our D term. And if we did not have feed forward, we would literally just say motor power equals PID, and then we would done with it. That is our main PID controller. But because we're adding feed forward, we've got some gravity, we need to be able to actually start feeding that in now. So for our gravity, it's effectively our feed forward term is going to be equal to our gravity constant, which is how much power we need to be able to fight off when we are at a pure 90 degrees or parallel to that ground plane. Yes? So our F term is going to be our gravity term multiplied by the cosine of our current arm angle. And this will figure out how much area under that curve we actually have, or sorry, underneath that triangle that we actually have. Then when it comes time to actually do our motor power, our power is going to be equal to our PID plus our feed forward term. And then we would simply run our motor at our power. There's a few other safety checks we're going to add in later with some sensors, things like that. Make sure that we know that our arm is either at rest or at our complete goal with some sensors to be able to do that so that we don't have our power moving past our kind of hard-coded limits. But as far as things go for our programming sense, that's how our PIDF controller is going to work. Now, there are more advanced ways of doing this, but as a base starter for something that works pretty darn well for most of what it is you're trying to achieve, this is a great way of being able to figure out an arm that is going to be able to fight some gravity at a fixed length. Now, one thing to note about this, with our feed forward term or K gravity, it currently does not allow for an arm that is capable of extending beyond its current points. We just assume that our arm is just a fixed distance. We're going to have another tutorial in the future about how you might change this feed forwarder's K grav based off of if you have some sort of telescopic arm as well. So keep an eye on that for the future. Now, just a quick reminder here. I'm going to be programming this in Android Studio for an FTC Rev Robotics Control Hub context, but the logic is the exact same. So whether you're using something like CircuitPython, Raspberry Pi, an Arduino, whatever have you, whatever language you're using, the way you write it might be a little different. Like if I were to start speaking, say, Dutch or French right now, the way in which I say it is a little bit different, but the main logic still applies here. So we're going to start off with making a couple classes. It's always best when we're writing things for robots to be able to separate our mechanisms and our assemblies out into individual classes. So I'm going to start by making a new Java class, and I'm going to call this one my pivoting arm. We're going to call this one our pivoting arm Teleop, because this is what we're going to run for the actual main program, and let's make the actual class for a lot of the logic for that arm itself. So we're going to call this one our pivoting arm assembly. And we're not going to extend anything. And later on in this tutorial, as I was talking about in that graph section earlier, you're going to have to be able to tune those KP, your KI, your KD, and your K gravity feed forward constant. You can set this up that if you were to say use something like a controller, you can then use A buttons, B buttons, X buttons, D pads. You can use your joysticks and your triggers or your buttons to be able to adjust and configure these things in your screen. but it's way easier if you can do those in real time. And I'm going to be using something called panels to be able to do that. But there are also other softwares that exist, things like FTC Dashboard for an FTC specific context that effectively allow you to do what's called like a hot swap or a hot fix or a hot adjustment of those specific values. You can adjust them while the program is actually running. So I'm going to write in at configurable, and that's going to pull in a specific import here for my panels class. Now you have to have panels installed specifically to be able to do that. I've got a video down below on my PagerPath tutorial on how to actually install that panels for you as well, if you're unsure how to do that. Now the first thing we're going to start setting up is our ARM encoder. Now, if you remember, I have an external encoder on my ARM. So because I've got a large gear ratio going through for that pivoting arm, rather than using the encoder on the motor itself, we're going to use that external encoder, which is a through-bore encoder. Robotic sells a through-bore encoder. Andy Mark sells one, but this one's basically from East Loop Components. And it's just a much easier way of us keeping track of where in space our arm is. So we're going to make a new private double, and we'll call this one encoder ticks per rev. And in my case, it is 4,000 for the East Loop Components encoder, because we have 4,000 ticks per revolution on a quadratic encoder. You need to look up your specific documentation if you're going to be using one of these. If you're just going to be using the motor encoder, you can go ahead and adjust this, or we'll get to that later as well. Now, the next thing we need to know is our arm angle relative to the ground plane at rest. So when our arm is all the way down at the bottom of our adjustment, where is it actually going to be in physical space? So if our ground plane were here and our arm actually rests lower, like mine does be otherwise, that'd be a negative angle. If our ground plane is here and our arm rests at 0 degrees, then that's what that's actually going to be. So we're going to make this, oops, not public, a new private double, and we're going to call this one angle underscore degree at 0 ticks, or we could call it at rest, whatever it has to be. I cannot spell today. We'll call this one angle degree at rest. And for me, I've already measured this out in my CAD program, and it's negative 15 degrees from that rest angle. We're going to use this later to be able to calculate out what our actual degrees are from 0, so we can figure out what that gravity constant needs to be related to how far up it is to go. If you don't have this on a CAD program, which you can also do as well, many phones have the ability to track angles on them, which is generally good enough for this case. So you can just take your phone, open up an angle finder app, slap it on top of your arm, put your arm at rest, and then figure out where your arm actually ends up resting at. And that's a great place for you to get that resting degree as well. Then we can actually get our actual main encoder ticks as well. So we're going to make this one a new private static. We're going to call this one an int, and we're going to call this one min position ticks. And we set that to 0. As well, we'll do the same thing for a private static int, and we're going to call this one, max, I cannot type today, position ticks, we're going to set this something arbitrary for now. I'm going to set mine to something like 1,500. I'm going to put in a quick to-do, tune this later. And effectively what we're going to do is we're going to take that arm, put it at a rest position, 0 out our encoder, move our arm all the way up to the maximum position it's capable of moving to, and then getting those ticks as well from that encoder. Next, we'll set up our KP, KI, and KD, as well as our feed forward. So I'm going to make this a new private static. We'll call this a double. We'll call this one KP, and we'll set it to something like 0 for now because we're going to tune these later. We'll do another private static double. We'll do KI, again, 0, private static, double KD, again, we'll set that to 0, and then another private static. I cannot type today, but we'll fix that. We'll call this one KGrav. Again, we'll also set that to 0. I'm going to adjust this so that it actually types in properly there. So now we've got all of our KPs and our constant setup. Well, again, we're going to tune these later. Next up, it's a good practice in robotics to keep track of what a max power output for your motor might be. So we might make this a private static double called max power. We're going to set this something like 98%, so that our motor can't ever go above 98%. When I'm first tuning, I like to set this something at like 0.8 because or when you're first running a system, you've never run it before, it's typically a bad idea to be able to run things at full power because that can cause some issues, particularly if something isn't assembled correctly, something blows it out of the way, or whatever it may end up being. Now we need some sort of anti-wind-up system here. So for that anti-wind-up, we're going to make a new private static double, and we'll call this one max I sum. And in order to figure out what a rule of thumb might be for this max I sum is we have to think about how long is it going to take for my motor to get from 0 to my end position. And based on our pretty heavy gear down in this system, I think our total is something like, I can't remember off the top of my head, it was like 1 to 120 or something like that. It could take realistically 2 or 3 seconds to get all the way up to that top. So we don't really want an integral sum that's going to be much greater than if it were to say maybe 1.5 seconds for that to go over. Otherwise, we end up getting these huge kind of wind-up sums. So I'm going to set mine to about half of what my encoder ticks per revolution is going to be. Because if it takes us, based off of 1500 to get from 0 up to the top, takes us 2 seconds to get all the way up there, that means that it probably takes us about a second to go through 750. So I might, set my max integral sum to something like double my maximum post ticks based off of the speed for mine. If you have a much quicker arm or a much lower gear ratio or a much lighter arm, you might want to start with something a little bit lower on this max I sum as well. And then we got some of our motors to set up here. So we'll make a private DC motor EX, and we'll call this one our pivot motor. And then we're also going to make a private touch sensor. Oops, that has to be a capital. Touch sensor, and we're going to call this one our magnetic limit switch. And again, that pivot motor is obviously the DC motor that's going to be rotating the main arm. And then this magnetic limit switch is the one that keeps track of when our arm is all the way at rest down at the bottom. There's going to be a few more helpful variables we're going to end up setting up here as well. We're going to make a private int called target position ticks. We'll set that to 0. So that just helps us know what is our target, where are we trying to get to. Or make another private int called current position ticks, and we're going to set that to 0 as well. We're going to do another one as well, a private double called last error. We're going to set that to 0. That's going to be helping with our derivative calculations later. Another private double called integral sum is going to be set to 0. We'll make another private boolean for was at meg limit. And we're going to set this one initially to false. And what this is going to let us keep track of is going to say, have we reached our bottom of our limit? Because once we get our arm all the way down to rest, we're actually going to reset our encoder so that our encoder always makes sure it's back at 0. So we have some external sensor verification beyond just our motor encoder to know that we are back at rest. And this power is just going to be the eventual motor that we're eventually going to be sending out. And then lastly, we're going to make another private elapsed time called timer. And this is just be equal to a new elapsed time object. And this is going to be able to keep track of how long of our loop times we're going in that update. Because again, we need to be able to keep track of our delta time, how long it's taken since we've last done a loop update over time, because some things might slow our loop down a little bit more. So we want to make sure that we're adjusting things based off of time rather than just off of what a last value might have been. Now that's a whole whack load of things to get set up. Don't worry, we're going to keep going through once we have all that kind of main logic set up. Now we'll make our constructor method to be able to actually build this class inside of a Teleop. So we're going to make a public void. We're going to call this init, and we're going to pass in a hardware map object called hardware map. We're going to say that our pivot motor is equal to our hardware map.get, and this is a new DC motor x.class, and I have called my arm pivot, but of course you should write in whatever you have written for your arm in this case. Now we're going to say our pivot motor.set direction, and in this case mine is direction reversed. You of course might need to swap yours around for forward. I've already verified that before. It's a really good practice when you're running this. Put your arm at about midpoint, run a power of like 0.1% in a different value so you know what direction your motor's actually going to be rotating. Even better if you can do this when it's not attached to your robot. Don't forget, when you run it through a geared system, you are going to be swapping that direction as well. So keep that in mind. You don't want to run things at full power on their first bore if you don't know it's going to be doing the correct direction as well. We're also going to do our set zero power, where did that zero power behavior, and I'm going to set mine to break. Now, there are two different types of zero power behaviors you can set in the FTC library. You can set to break, or you can set to float. And this means that if you were to stop or set your power to zero, that the motor is going to hold its position as opposed to free floating along. And because this is a pivot arm, of course, we actually want to reset that. Next, we're going to do our pivot motor dot set mode. We're going to stop and reset the encoder, and then we're going to do our set mode, and we're going to say run without encoders. Oops, there it is. Now, it seems a little bit strange that we're going to stop and reset the encoder, and then we're going to say run without the encoder. Wouldn't that mean that we're not actually able to read our encoder port? Not actually true. You can still read the encoder port in the FTC library, but it does allow us to, rather than using the built-in PIDF controller on the motor itself that's built into the FTC library, we're going to be writing our own PIDF controller for this. So this allows us to basically set that up. So we don't have to worry too much about that. We can still read that external encoder as well. Or if you're going to be reading the encoder on the motor, this still works if you happen to not have a through-bore encoder for this setup. Next, we're going to set our magnetic limit switch. It's going to be equal to a hardware map.get. And this is a touch sensor. And our touch sensor here, in my case, mine is called arm_meg. Oops, it's touch sensor.class, my mistake. And it seems weird this is a magnetic switch. You can also set up as a digital object. Just keep in mind that it's actually going to read false when you're not attaching it and read true when the magnet is in front. So you need to swap your logic around if you're going to set up as a digital object. So setting up as a touch sensor is totally fine. Despite it being a magnetic limit switch, it still is programmed the same thing as a touch sensor. Then we're going to zero a few positions. So our target position ticks is going to be equal to 0, and our current position ticks is also going to be equal to 0. And then we'll go ahead and make our timer dot reset so we can reset our timer when it's inside that start of our loop as well. Now, if you happen to initialize and then not start things right away, you can end up with a pretty large timer boom right at the start. So we're actually going to make a new public void called start. And we're not going to pass anything in. And in this, we're simply just going to call timer dot reset as well, just in case we happen to not have that reset here. And this just basically ensures that our timer starts at 0 when we start our program. So now comes time for the actual meat and potatoes of our program, which is the main update loop. And this is a kind of state-ish in its base machine, but we're basically going to update our arm once a loop so that we can have that subassembly basically running the way we want. So we're going to make a new public void. We're going to call this one update. And we actually don't have to pass any information into our update inside of our loop either. So the first thing we need to do is we need to get our delta time. So make a new double called delta time. You're welcome to also call this DT if you want to use short form programming. I'm making it long form because I think it's a lot easier to understand in an abstraction base when you want to look back at this later to not have short form writing. And we're going to grab our current timer dot seconds, so we know what time has passed since the last loop. And then we can go ahead and call timer dot reset to adjust our timer basically right away. Next, we figure out where we currently are. So our current position in ticks is going to be equal to our getting current position. Now we haven't actually done that yet, so let's make a quick getter method here. So we're going to make a new public double called get cur position in ticks. And we're simply going to return our pivot motor dot get current position. So here we're going to set our current position ticks to our get current position ticks. Sorry, we actually had already written one of these, so it actually should be current because we already created that. And this is going to be a public int, not a public double. My mistake. So now we actually have our ability to get our current ticks. Now, if you're wondering, why did I bother to take that, put it inside of another method as opposed to simply calling it here? Reason being is this allows us to get our current ticks in another class or a Teleop class or autonomous class in the future if we want to, so that we can access it without having to call our update every single time. It just makes life a little bit simpler to be able to do some debugging in the future. Next up, it's time to calculate our error. So we'll make a new variable called error. And our error is equal to our target position ticks minus our current position ticks. So where we want to go to minus where we are. Then we can actually calculate our p term. So this is our PID controller section now. Make a new double called p term, and our p term is equal to our error multiplied by our, not our KD, our KP, which of course is pretty simple. So now we can go into our integral at this point, and we're going to take our integral sum is going to be range.clip. And effectively what range.clip allows you to do is it allows you to put in a band for that. So it allows us to say, hey, you want to make sure you're not going above that maximum integral that we set up earlier for the sum we're allowed to have, or the minimum integral sum that we're allowed to have. So what a clip lets us do, it takes a value as your first argument, and then your minimum and your maximum. And similar to our flowchart, well, not similar exactly as our flowchart, we're going to take our integral sum plus our error multiplied by our delta time is our first argument. Our second argument is a negative maximum I sum, and our last argument is a maximum I sum as well. And then we can make our now I term, and our I term is simply equal to our integral sum multiplied by our Ki. So now that we have our integral set up, we can now start actually doing our D term. So we'll make a new double called D term, and we'll initially set this to 0. Then we're going to check if our delta time is greater than 0. Again, rarely will you ever have a loop that happen to be exactly 0 seconds, but it's always good to check, because if you do end up having a delta time that is 0 on the off random somehow chance something flips an integer here or flips a bit somewhere, you'll end up dividing by 0, which of course will immediately crash your program. Not a great place to be. So for the amount of time that it takes to actually adjust this, doesn't really make much sense not to throw it in just as safety. So we'll then say that our D term is going to be equal to our error minus our last error outside of that first set of parentheses divided by our delta time And then outside of this one as well, we're going to multiply that by our KD to actually get our delta term. And then if our delta time happens to not be, then our D term will just stay 0. And after this, we can say our last error is equal to our current error so that we can figure out what our rate of change is earlier, similar to like we did up here above with our delta time and our timer reset. Now that our main PID section is done, it's now time to actually get into our gravity feed forward section of our PID controller here. So in order to do this, our double feed forward term is going to be equal to our K grav multiplied by the cosine of our current angle for wherever that arm is relative to the ground plane. So let's make a helper function to be able to turn that in because we're going to have to play around with some radians a little bit here. So let's make a new helper function down at the bottom. Make a new public double. We're going to call this one estimate angle radians. I'm not going to pass anything in. I'm going to make sure I capitalize that. And we're going to say our new double degrees per tick is equal to 360 degrees multiplied by our encoder ticks per revolution. In our case, that was 4,000. And then a new double called degrees from 0 ticks. So figure out how many ticks we are from that 0, which is our current position in ticks, multiplied by our degrees per tick. And then we can actually return what our current angle is. So we can return math.toRadians, and this is our angle degree at rest plus our degrees from 0 in ticks. So this will actually take out where we are relative to our 0 and then add in that angle degree at rest so that we can end up getting our current cosine position. And the nice thing about our cosine function is even if we go past our 90 degrees from the reflection, we'll actually flip our cosine down to then be able to start giving us an opposite angle for what it is that we need. So when we come back up to our K gravity at this point, it's effectively going to be our math dot cosine, and we will call our estimate angle radians. Now the last thing to do is actually to control the motor. So that's our simple point at the end here. We now have our F term done. We now have our PID terms now set up. So we can actually do our main power. So now just like that flowchart, we can just simply add up all of our terms. So our power is equal to our P term plus our I term plus our D term plus our feed forward term. Really simple. Now, good practice after this is to also clip the maximum power because it's possible that if we add up all of these P terms, if things aren't tuned properly or if we're really far away from our target, that we could end up sending a value that's higher than 1.0 or negative 1.0. So it's a good practice to clip your power. So we'll say that our power is equal to range.clip, and we're going to take our value of our power, and we are going to say negative max power, and then just standard max power as the other end, so that we will never send a value that is outside the limits of what it is that we want our motors actually accepting as a valid point. And then once we've done that, we can simply say pivot motor dot set power, and we'll simply set this to power. And that's it. That's our main update loop actually set up. Now, one of the things you're probably noticing as we run through in our main logic here is that we have no safety set up right now. So we haven't used that magnetic limit switch anywhere. We haven't really used that encoder anywhere to keep track of where we are over time. So let's actually start adding in some of those safeties so we can make sure that we're not going to go over or under our maximum retraction or maximum extension limits on that pivot arm. So let's go back in and let's add in some of these safeties. So once we're done doing our time, we're going to do a first meg switch safety check. And we're going to set a new Boolean called at limit. So this is whether we're at that limit switch or not. You could call this at bottom, whatever that might be, is equal to our magnetic limit switch dot is pressed. And this is going to return true when that magnet is in front of your Hall effect sensor, and false when it is not in front of that Hall effect sensor. So then we're going to say if we are at our limit and if we are not, we haven't, or the last state of that limit switch was not the same as what we're currently at. So basically this stops us from triggering this every single time we hit that limit switch. This allows us to stop some of that bouncing that sometimes can happen when you're running these. So if we're at the limit and this is the first time that we are at that limit, we're going to set our pivot motor dot set mode, not set power. It's going to be set mode, and this is going to be stop and reset the encoder because we're at the bottom. We're going to do our pivot motor dot set mode, and this is going to be run without the encoder. And then we're also going to set our integral sum should be equal to 0 because we've now set ourselves at rest. And then we can say there was at meg limit is current to the current at limit Boolean. So if we go through this logic, we read our magnetic sensor. If we are currently at the magnetic limit sensor and the previous value was not at the magnetic sensor, that means we touch it the first time, we're going to reset our encoder back to 0 because we've now gone back to the bottom. We're going to set ourselves back to run withouting, and then we're going to zero out our integral sum so that we also can make it a little easier to be able to bring some of those values back up. And then we keep track of what the previous state of the magnetic switch was. So when you go back up the loop, if we're still at the bottom, this will no longer run, and we're not going to be constantly resetting our encoder every single tick, which is actually going to end up causing some pretty serious problems if we were to run in through that. So now let's go in and add some more safeties here down near the bottom of our update loop. Before we actually go about controlling the motors, we need to apply some safety bounds. The first bound we're going to check is if we're at the bottom of our bound. So we're going to say if we are at our limit switch and our power is less than 0. That means that we have hit the bottom of our main safe limit and we're still trying to drive down. We're going to set our power to 0. So we're actually going to override what our previous power was. Oh, actually, I'm putting this in the wrong spot. Let's go ahead and cut that out because that is 100% not going to override the previous power. We have to make sure that is below our power equations. Otherwise, that isn't actually going to work. Then we're going to say else if our current position ticks is greater than or equal to our max position ticks and our power is greater than 0, this means that we have now hit the end position of our arm and we're still trying to push further than what the arm is capable of going itself to. We're also going to set our power to 0. So we'll also override what this previous power position was, and then we will actually run our main set power position at that point. So now that our main update method is done, it's time to make a few more helper methods for us as well. So right now we have no way of actually controlling the motor or telling it where to go to an actual specific position. So we're going to make a new public void called set target position in ticks. And we're going to pull in an integer called ticks effectively. And for this one, we're simply going to say that our target position ticks is equal to our range.clip. And again, it's going to be, we're going to take that ticks and we want to grab our minimum position ticks and our maximum position ticks so that an outside user could not possibly set a position that is outside of the bounds that we have set inside of this class for how far we're allowed to actually go. So we always want to clip that in. Now it's helpful to know what our current target is as well. So we're going to make a new public integer called get target position ticks. And we're simply going to return our target position in ticks, which was previously set up down above as well here. Oops, need to put in a semicolon. Now, one thing that I forgot to mention that you might need to check on your specific encoder is it's possible that the external encoder is reversed compared to your motor. In my case, it is. So in order to be able to swap that around, all you have to do is multiply your current position call by -1. If your encoder is not reversed, you obviously don't have to do that. But if you find as you're moving your encoder up and you find that your ticks are actually going down, simply multiplying this by -1 is going to help with that. And in my case, my encoder actually is reversed based off of the actual DC motor and its placement as well. It's also helpful if we have another couple, if you have a public double called get error, and we simply return our target position ticks minus our current position ticks for our error. And then again, as well, a new public double called get power. And then we simply return our power. Similarly, it can be helpful to get our integral sum as well. So make a new public double called get integral sum. And we will return our integral sum. And then being able to figure out if our magnetic switch is actually working or not, make a new public Boolean called is at magnetic switch, pass nothing in, and we'll simply just return our magnetic switch dot is pressed. So we know whether our magnetic switch is actually working or not. Now, last one, as a last point here, it can also be helpful to know what our current PID and feedforward values are as well. So we can go ahead and write getter methods for that too. So if I actually right click on Android Studio and I select generate, we can actually generate getter methods for our KP. If we hold shift, we can grab our KP, KI, KD, and KGrav as well, and then select OK, and it will automatically create our getter methods for us as well, which is quite helpful in this case. So that is our main class done. So let's go ahead and actually write this into a Teleop now. Now that we have all the logic set up to be able to run our program, it's time to actually make it do something. So let's go back into our pivoting arm Teleop, and this is going to extend our op mode. In my point, I always like to extend op mode as opposed to linear op mode, because I think it's a better way of programming robots based on how robots actually like to run, which is state-based machines, as opposed to more traditional programming, which is more standard. Oh, that's right. Yeah, and let's go ahead and import that class as well. And then we also need to write at teleop, otherwise this won't actually run. Now our extends op mode always needs two methods. It's going to be a public void, not void, init. And we'll just leave this empty for now. And we need a public void loop. And again, nothing inside. We'll just make it empty for now, just so it can stop. And then in our case, we're actually also going to use a start as well. So we make a public void start. And that's going to happen in an FTE context. When you press the actual play button to start, you will actually run your methods here. So we're going to pull in a new instance of that class that we just made. So we're going to make a new private final called our pivoting arm assembly. And we're going to call this one our arm. And this is going to be equal to a new pivoting arm assembly. And then because it's nice to be able to have some manual control, we're also going to add in the ability to manually nudge our arm up and down. So we're going to make this one a new private static int. We're going to call this one nudge underscore ticks. And we're going to set this to 20 ticks. So that will allow us to basically nudge the arm up 20 ticks at a time in the future. Inside of our init method, we need to actually run our initialization constructor method for that. So we're going to say arm.init. Not to get initial sum. We need to say arm.init. And we're going to pass in our hardware map as our main argument. And then we'll do telemetry.add line. And we'll simply pass in all arm mechanisms initialized. It's also useful for you to add in another line here, telemetry.add line, and I might add in ensure it happened when arm was at rest. Just as a sober second thought to make sure that our arm was actually down at the bottom before we actually run in this as well. And inside of our start, we're going to say our arm dot start so that we can reset our timer as well. And it's actually a good practice, something I forgot to mention earlier, to also set our target position back down to 0. So let's go back inside of our class here for our start. We're going to reset our timer, and we're also going to set our target position to 0 as well, so that we can stop and reset our encoder, as well as set our current goal to 0 so that we're not moving. So that automatically starts inside that start position. So if our arm happens to not be there, it'll automatically get ourselves all the way down there. So let's actually do some main control here. So this is going to be control the arm. And for our arm, we're going to say if our gamepad1.a is pressed, we're going to try to bring our arm back down to rest. So we are going to say arm.set target position ticks is going to be 0. We'll say else if our gamepad1 y is pressed. So if we press our top button, we're going to try to move ourselves up. So I'm going to say arm.set target position, and I'm going to set this to our maximum tick value. And because I can't remember what that maximum value was, I don't just want to guess here. So let's write a helper function to allow us to maybe use a scale that makes more sense, like a scale of 0 to 100. So let's go back to that pivoting arm assembly here, and let's make a new public void set target position percentage. And we're going to pass in a new int called %. And what this will allow us to do is allow us to set the target position as % goal rather than as a tick. And this will help us kind of abstract out some of that complexity later on in that. So we're simply going to say that our target position in ticks is going to be equal to our range.scale. And what scale allows us to do is allows us to take a value, which is going to be %, allows us to take an old range, let's say it used between 0 and 1350, and scale it to a new range of 0 to 100. So in our case, our old one is our is our minimum position ticks to our maximum position ticks. And then our new minimum is 0, and our new maximum is 100. And because these are integers, we're going to turn that into an integer as well. So I'm realizing as I was doing some editing, I made a pretty big mistake on our scale here. This should actually be in reverse because we are going from 0 and 100 scale to our minimum and our maximum scale. So definitely did that in reverse, but we'll go ahead and make that change now. Not going to be a problem for you, will be a problem for me in the future when I start tuning. So now when we come up here to set our target position ticks, we can now set our target position ticks as a target position percentage. And I did not spell that right. And we're going to set this to say 50% just as a quick and dirty. You're obviously going to have to figure out where you want to set these things to go. But for now, we're going to do 50 just as a quick test to get ourselves to the middle of the range, because when we're testing, we don't want to actually send ourselves up all the way to the top, because that would be a terrible idea. And once we've actually decided to tell that arm where to go, we have to make sure we're updating that. So we're going to call arm.update. So we're actually making sure we're actually telling the arm to actually move to those positions. And at that point, that's all we need to do to be able to get our system up and running. But as I alluded to earlier, it's nice to be able to have that ability to do some manual adjustments as well. So we're going to add the ability to do some manual adjustments as well. We're going to say if our gamepad 1 dot D-pad down was pressed as opposed to is being pressed. That allows us just to tap it once as opposed to holding it. So if our D-pad down was pressed, we're going to say our arm dot set target percentage. Well, actually, no, we're going to do our set target ticks, and we're going to pass in our arm dot get current position ticks, and we will minus our nudge ticks. And then we'll do the exact opposite logic on the other side. Else if our gamepad 1 dot D-pad up was pressed, close that off. Then we'll set our arm dot set target position ticks is going to be equal to arm dot get target position ticks plus our nudge ticks. So that will allow us to basically nudge our arm up or nudge our arm down, depending on whether we're tapping that D-pad up or down to get a little bit more of that fine adjustment. And then it's always helpful to have a little bit of telemetry updating in here as well, because otherwise right now we're working with a little bit being blind. It's not very obvious what things are working on. So let's go ahead and add in some more telemetry data. So just as some final telemetry data to add in there, we're going to get what our current position in ticks is, what our target is, what our current error is, what the current power we're sending, whether our magnetic switch is being activated or not, what our current KP, KI, KD, and KGrav as well, and then what our current integral sum is. This one is particularly useful because it allows us to check if whether this maximum integral sum is way too high or way too low in that respect in order for our integral to actually do anything. So now that we've got that all set up, we should be able to actually go ahead and run and start tuning this process. So let's head on over to the robot, let's build this, and let's go do some tuning. All right, so let's get started with the actual tuning process. Now, you're going to need some way to be able to change, as I alluded to earlier, be able to change these KP, KI, KD, and KGrav while we are actually working on the arm. You can do this with using just some D-pads. So if you press D-pad up, down, left, right, whatever, you increase and decrease your KP and KI. However, I'm going to be using panels as a dashboard for this instead. So I'm going to go ahead and connect to the Wi-Fi network on my robot, and then I'll also connect to the Wi-Fi network on Android Studio. Now, this part is not actually necessary to connect to your Rev control hub via Wi-Fi to be able to do this, but you do have to be connected to the Wi-Fi network on your device. So I'm going to go to my panels dashboard, which is HTTP, not HTTPS, 192.168.43.1, and then port 8001, and that opens up this little dashboard here, which allows us to edit some things on the fly. Now, as a reminder, we are using the pivoting arm assembly as the class. So if I come down to the pivoting arm assembly, we can now see the variables that we've made static, and we can now change these on the fly. So on our driver hub here, I'm going to go ahead and activate this Teleop. So the very first thing we need to do is we need to figure out what our maximum position is on these ticks for these arms. So we're going to be running our program, and I'm just going to manually actuate the arm all the way up to the top. Oh, and there's a lot of torque on this thing until we get to our full rest. Now for me, my full rest is about here because I've actually got a hard stop that doesn't allow to get past here. And now when I look at my driver hub, because we're printing out what our ticks are, our current arm ticks are 1443. So if we go back into Android Studio, we can now go to our pivoting arm Teleop, and our pivoting arm assembly, and we can now change our max post ticks. Now 1443 is the maximum we get to. So I'm actually going to set this to 1400 because I don't want to actually go back and past that main sort of loop. So now that I've got this fully set up from a mass post ticks, we can go ahead and build this. So let's build this program over. We will reset our arm back to 0 so that it's back at the initial starting point. And then we can start with actually tuning our KP. All right, so now that we have our max post ticks, or the maximum position in ticks, if we press Y, we should see that our arm does absolutely nothing. Our current arm target is 700, and our current arm error is 700 as well. Reason that our arm doesn't do anything when we press Y to go up, and then A to go back down, is because we presently have absolutely no KP. So we're going to start with 0.001. So we're going to start with a really low percent, or 1% power. And we will load that in. Now we press Y. Should be able to observe our arm. And rather slowly gets there. And our current arm error is about 200. Our current ticks are 500. And our target is 700. So we're about 200 ticks away. So we'll bring it back down. So this is probably too low. Let's go to 0.002. We'll press Y. And our current error is now at 81. So what we're doing right now is the entire process of tuning this KP is we're going to lift the arm up and then observe what the error is and then bring the arm back down so that we can then change what our KP values are going to be. So presently, if I press up, our error is 72. So I'm going to bring it back down. We'll bring this KP back up again. We'll bring up, and our error is now 49, but we still can't quite get to where it is we're trying to shoot. So I'm going to keep bringing this KP back up again. We'll bring it back up. Again, observing the arm, observing the error. Error is now down to 28. Still a little bit low. Let's bring this up again. Bring it up. Error is down to 21. But we have yet to overshoot, so we can probably keep going again. And what we're doing is we're trying to get our error as close to 0 as we can without actually overshooting what that's going to be. So our error is actually 4, which is pretty darn impressive to have such a quick error just at that KP. And probably part of the reason why this is so successful right now is we have such a low gear ratio that that's going to work quite well in this respect. So now we've got our KP pretty close to what it is we're shooting for. I'm actually going to drop the KP back down a little bit to something like 6.5 and then bring it back down. And the reason I'm going to do that is because now it's time to tune our K-grav. Okay, so we're going to write this value down for KP of 0.0065. So I'm going to write that down in our actual main class here. So our KP of 0.0065 was pretty good. The reason I'm writing that down is because these are hot fixes. So if I were to run the program again or stop it, it wouldn't actually change anything. So now we're going to bring our KP to 0. At this point, we're going to start tuning our K-grav. So I'm going to attempt to lift our arm up here to our 90-degree position. And we're going to see that the arm is slowly falling down anytime we have it at the position. So now we're going to simply increase that K-grav until we get to the point where that arm is no longer falling down when we're at 90 degrees. So now we're going to give it, say, 1% power. That's probably going to be too low, I'm going to guess. And if I let go, the arm wants to fall down. So we will increase that again. I'm going to go to something like 0.03. And that's actually pretty darn close. Well, if we get to 90 degrees, it's no longer falling down. So this is our constant that we're going to be using of 0.03 for our K-grav. So I'm pretty happy with that. And that's going to be that part that's going to be linearly interpolating in to be able to get ourselves based off of where we are in the ground. So K-grav of 0.03, or it takes about 3% of our motor power. Put that in. We'll add that back into Android Studio here, 0.03, so that we don't lose that work again. And then we'll put our KP back to 0.065. And we'll bring it back down and up and back down. And again, we're going to observe what that error is going to be as we go. And overall, pretty darn solid with just a simple proportional control system. Now, if we had a much higher gear ratio, or sorry, a much lower gear ratio, we will likely have to do a little bit more tuning than this. And if we had a much heavier arm, probably have to do a little bit more tuning on this as well. But now we can go ahead and do a little bit of derivative. So in, of course, our derivative point here, derivative is, of course, that damping force. So as we increase that derivative, you're going to notice that we are going to get a little bit more of a slow stop to get there. So let's go to something like 0.002, something relatively low, or 0.001. That's actually a pretty high derivative to get started. And you notice that we start to jitter coming down. Way too high derivative. Let's put another 0 in there. Come back down, come up, and back down. And we see we don't actually have any jitter anymore. And we have a slow or a little slim little bit of reduction as we get into that top point. So in this arm, pretty decent derivative. I'll go back to that too high derivative just so you can see that again. So you'll definitely know when your derivative is too high, and having too low a derivative is not really a problem. You're just not going to have a huge damping force anymore. So we can see that we get a little bit of slowdown on that arm as we come up. And the last one to do is our KI. So presently my arm error is 12 ticks. I have a target ticks of 700 and my current ticks are 688 and my error is 12. So if we were to increase our integral sum, right now our arm integral sum in ticks per second is about 500 and it's increasing by 3 every single sort of about half second at the moment, or every single loop it's increasing by 3 because we're not able to actually get to our target goal here. So if I were to add something like 0.0001, and that I did it, and we're actually going to start increasing our integral at this point, and we're going to get closer to our target, but get rid of those last couple ticks. And that's probably too low, and we can leave our arm in this position and, slowly increase our KI until we're able to get to no error. And right now our error is now at 0. So I'm going to bring it down, and we'll bring it up. And our error is at 6. And we'll bring it back down and bring it back up. Our error is down at 3, 2, and then we might increase that just a little bit higher to be able to get our error just a little bit low. Let's make sure we have written down these values before we go any further. So I have my max position ticks is indeed correct. My max power is fine. My max I sum. I might bring this down a little bit because we got a pretty wild swing from that integral. And we definitely don't want having such a wide swing here. So our K grabs 0.03. Our KD should be something more like 0.0001. And then we're still tuning our KI. In this case, we might have something like 0.0001. I might throw in another 0 on that just because with our integral, we really don't want to be swinging around like crazy. So let's go ahead and initialize our program again. Our robot is at rest, and we'll save these two values over. And now as we swing up here, again, probably too high. An integral swing there as well. Okay, so turns out my problem actually was my encoder got unplugged somehow. I didn't have that fully plugged in. So it actually wasn't a wild integral swing. It was more the fact that we just straight up didn't have our encoder plugged in. So if we bring that integral back up, we can now get our error probably a little bit too high. So let's put another 0 on there. We'll bring that up. And that's going to be a pretty solid integral. We've got an error of about 2, which I'm pretty happy with. An error of 2 ticks. I don't think anyone would have any problem with one of those. So that's, now that we've done that, we'll go ahead and actually save off our last K integral here, which actually we have done. And now we've got our arm tuned. So now you're welcome to go ahead and use your D-pad to start nudging your arm all the way up and giving it a little nudge to come all the way down. And you can move your arm to any position, even straight 90 degrees, and it won't fall down past what it is that you are shooting for. And you can still move quite quickly. So I hope you found that a helpful tutorial in going through KPKD. If you have a much lower gear ratio than I do, You probably have to spend a little bit more time tuning on this, because honestly, even just proportional control was really solid for this system, for what it is that we need it to be doing. If you'd like access to this code snippet or the CAD file for this whole robot down, you can find that in the community link down below, as well as any other resources that I've made in the past for other tutorials. If you got any questions, let me know in the comments. I'm going to do my best to answer those for you. And as always, best of luck in your next robotics project.